Hello, everyone. Welcome back to our class. We're going to continue with our quick introduction to algebraic geometry. And the goal of this quick introduction to algebraic geometry is just to introduce the main concepts that appear in the definition of elliptic curve. So an elliptic curve is a smooth projective variety. So last time we started talking about projective space. Today we're going to introduce varieties. We're going to say, what does it mean for a variety to have dimension 1? We're going to say, what does it mean to be smooth? And then next time, we'll talk about the genus of a variety, of a curve. And well, we know what it means to have at least one rational point. So last time, we saw affine space. And we saw that we defined projective space. And then we defined also what are an algebraic set, an affine algebraic set, what is an ideal, the ideal attached to an algebraic set, and then what does it mean for an algebraic set to be defined over K? In principle, they're defined over K bar, but if there are defining polynomials that are defined over K, that the coefficients are in K, then we say that the variety is defined over K. We're interested in number theory here, so we don't want to always work over an algebraic closed field. We do want to work over Q or FP or other fields that are not algebraically closed. So what we're going to do today is talk about projective algebraic sets, varieties, the function fields attached to varieties, dimension, and maps, morphisms, and things of that sort. We had some running examples. We talked about the y-axis last time, which is given by the ideal x inside the polynomial ring in two variables. And then we also talked about the algebraic set given just by 1 point, and then found that the ideal is generated by xy. There was a question last time about how do you identify if a given set is algebraic or not. So let me pose this question: are the integers an algebraic set within the affine line? So let's see what the answer to that is. All right, so let's start there. So are the integers, the set of integers, an algebraic set? And the answer is no. No, that is not an algebraic set. How would you go about it? How would you go about showing that it is not an algebraic set? As I said last time, you try to find what would be the ideal of such an algebraic set and prove that we reach to a contradiction. So if it was, let V be the integers inside the affine line, and then there would be, if it was, then there would be an ideal, which is an ideal in Q bar X, right? And but we know that this is a PID, so that tells me that this is a principal ideal. So there is a generator F that satisfies the conditions that it has to vanish at all the points in V. So in particular, so if n is in Z, which is our algebraic set, allegedly algebraic, then f of n would be 0 for all n in the integers. But that means then that f of x is a zero polynomial, identically 0. You can show this in two ways. For example, f, if whatever the degree is of f, d, it can have at most d roots in Q bar with multiplicity, but we have infinitely many. All the integers are roots. Otherwise, you can also show that, well, if n is a root of a polynomial, then x minus n would divide that polynomial, and then you have all these infinitely many factors of x minus n dividing the polynomial, and that would be a contradiction. So f is the identically 0 polynomial. Let's see what is the algebraic set attached to the ideal 0. Well, every number in Q bar is a root of the 0 polynomial, so this actually corresponds to all of Q bar, which is not the integers. So we've reached a contradiction, and therefore Z, the integers, are not an algebraic set. In general, an algebraic set is a set of roots of polynomials. So there are going to be either finitely many points, or they satisfy some algebraic equation, and the integers, there's just infinitely many points, and they're not going to be the roots of one single polynomial. Okay, so what are we going to do next? Then we have to, well, we defined, last time we defined algebraic sets, affine algebraic sets. So we're going to start today with defining projective algebraic sets. So here we go. So so if we're going to define a projective algebraic set, then what we need is, like before, an ideal. But in this case, the ideal is going to be a homogeneous ideal, which means that the generators of the ideal are homogeneous polynomials. Okay, and then the set of all P in projective space such that f of P is 0 for all f in I, this is a projective algebraic set. Okay. Conversely, if V is a projective algebraic set, then we define the ideal of the projective set as those polynomials where f is homogeneous and f of P is 0 for all P in V. Okay. Okay. So let's see some examples. So for example, let's write some examples here. So we have, like last time, let's start with the y-axis. So we had an ideal x, and now in projective, in the projective plane, we have 3 variables, x, y, and z. A bracket there. Bracket is here. Okay, and the ring of polynomials in 3 variables, x, y, and z. We have the ideal generated by x, and what that gives me is an algebraic set, a projective algebraic set, which is the zeros of the polynomials on that ideal. So the x coordinate has to vanish. So those are the points with x equals 0, and then b, c, such that b and c are in Q, and not both 0. When you define projective space, remember that you have to, we don't consider the 0th vector. The 0th vector doesn't define a line through the origin. So that's what that star is about. Okay, so we have that, and those are the points in P2 that correspond to that ideal, and that is an algebraic set, a projective algebraic set, and it corresponds to a line in the affine plane, the y-axis. By the way, note that something that is actually relevant to elliptic curves is that the point 0, 1, 0 is in there. And in fact, for every vertical line in the affine plane, or in the projective plane, the point at infinity is 0, 1, 0, every vertical line goes through that point. So I'm going to make a note of this because it's going to become useful. So I'm going to call this one O, and this is in all vertical lines let me check that that is actually true with another example. So if I want to write down the line x equals a, so if it was the affine plane that I'm talking about, then what I would like is the ideal generated by x minus a. But you see, we actually want this to be a homogeneous polynomial, so the homogenization of that polynomial, which I'll talk about in a moment, is x minus az. And again, this as an ideal in this ring of polynomials. This ideal gives me a projective algebraic set, let's call it, let's fix A0, saying Q. This is going to be A0, so A0 is fixed, and then I can run the B coordinate anywhere I want. But if this is X is A0, then for this to vanish, Z has to be 1. So this is not all the points, but almost all the points in there. For any B rational. And the point I might be missing is if Z is 0. If Z is 0, then the definition of the ideal tells me then for that to vanish, X has to be 0 also, and then the y coordinate can be anything, but because it's in projective, I can divide by the y coordinate, and that's just going to be the point 0, 1, 0 in projective coordinates. Okay, so you see that again, this is O, and it is again in VI, which is an projective algebraic set that corresponds to a vertical line in the affine plane going through the point A0, 0. Okay. All right, let's do something else, another example. We also had last time the ideal xy, that is also a homogeneous ideal inside Q adjoint x, y, z. That is also a homogeneous ideal. And here also, let's see what is the set that it generates. The algebraic set, x has to vanish, y has to vanish, and then z can be anything. But again, this is a projective point, and 0, 0, 1 is the same as 0, 0, 2 because I can scale. So the class of this point, there's actually just one class. So there's only one point, which corresponds to the point at the origin in affine coordinates. All right, so this is 1 point. The algebraic set is just 1 point. Okay, so yeah, let's talk about going from projective to affine and from affine to projective, which is the following discussion. So let me start. Maybe I'll put a header here from affine to projective and back. So let's start with an affine algebraic set. For example, we're interested in what's actually an elliptic curve. We'll see that is an elliptic curve. The elliptic curve y squared equals x cubed minus x. So that is given by the ideal, by this ideal in Q xy. Okay, so that the affine algebraic set attached to this is rational pairs such that b squared equals a cubed minus a, right, in A2. Okay, or in other words, this VI defines the curve given by this equation in the affine plane. Great. So now what I would like to do is homogenize to find what we call the projective closure of my curve. So this is a piece in one, this is a piece in what we call an affine patch. And then what we want to do is find the projective closure in all of P2. Okay, so to do, so if you have a curve, we have a, a curve in the plane that is given by f of x, y equals 0, the projective closure is going to be given by a polynomial f star in 3 variables now, given by z to the degree of f times f evaluated at x over z, comma, y over z. Okay, so let's do that for our curve here. So what I get is that f of x, y, I'm going to take it to be y squared minus x cubed plus x. And then what I find is that f star is, the degree is 3 times f. So now I'm going to evaluate this at y over z squared minus x over z cubed plus x over z. And when I multiply through by z, what I get is z y squared minus x cubed plus z squared times x. Okay, and that is my my new curve. So now the projective closure is given by the ideal ideal generated by z y squared minus x cubed plus z squared times x, and that gives me a projective algebraic variety. I'm gonna just call it. That's not very clear right there. I'm going to call it VI projective, and that is going to be the set of A, B, C projective points such that they satisfy that equation. Okay, such that f star of A, B, C is 0. Right, great. So this is now the curve in projective space and is given by f star equals 0. Okay, here this equals 0. Great. Now I want to go back and also again I can go back and retrieve, if I have a projective or a projective algebraic set, I can retrieve affine copies of it or affine pictures, so sort of like slices of my projective object by taking their intersection with what we call affine charts. So, let's write here what affine charts are of, for concreteness, let's just do affine charts of P2. So P2 is all the points of the form A, B, C, right? With some just the usual relation in the quotient, and then what we can do is, so you see, we can fix the z coordinate to be 1. Okay, in this case, the points with z equals 1, and then what I get is these points, the A, B1 in P2. These are now in correspondence with the points A, B in A2. These are not all the points in P2 because they're missing points with coordinate equals with z coordinate equals 0. Okay, so it's not all of them, but it's almost all of them. It gives you a big picture, which is in the affine and where we're more comfortable living. But that is an affine chart. Okay, so this is what we say is that this is isomorphic to A2, and we call that the affine chart corresponding to z equals 1. But there are more affine charts. So for example, I can pick the affine chart with y equals 1, and those are the points A1C, which is also isomorphic to some A2. And we can do many of them with other linear combinations of x, y, and z, but like the main charts are these three ones. Okay. Okay. So now what we're going to do, an affine chart of an algebraic set is V intersect with these affine charts, with one of the affine charts that are in Pn. Okay, so let's do this affine chart business for our example. So if we start from, remember, a projective algebraic set, in this case was given by z y square equals x cubed minus z square x. Okay, I'm going to do an affine chart. So I'm going to look at V intersect the affine chart given by z equals 1. Then what that is those points in there that have this property. So they have to be of the form A, B. I'm going to actually change it so it's more clear. So are points of the form x, y, 1, such that what? Since z is 1, I can actually say these are the points that satisfy y squared equals x cubed minus x. Okay? Because these have to satisfy the F star condition, but the F star condition when z equals 1 reduces to this one. And this is the original algebraic set that we started from. Okay, the original affine algebraic set we started from, but we can do other affine charts which make the curve look a little bit different, but it's still the same curve. Okay, so now I'm going to do, how about we check what happens in the chart when x is 1. When x is 1, I have 1 y z, and now they have to satisfy that z y, let's do lowercase letters here, that z y squared equals 1 minus z squared, or if you want, that z y squared plus z squared equals 1. Okay, so that now it looks like a very different curve in A2 in the affine plane, but these are actually isomorphic. These charts are isomorphic, and there is a way to go from one to the another. There's some rational map to go from one chart to the other that gives you some correspondence between the two charts, and then you can do this with other charts. Okay, so let me give you one more example about charts that is interesting, I think, which is what happens, for example, with conics. So let's start with a projective algebraic set given by x squared minus y squared equals z squared. Okay, I can do a projective. I can do a chart. I'm going to intersect it with z equals 1. And then what happens is that, well, z equals 1 is going to give me the chart that looks x squared minus y squared equals 1. All right. That is a hyperbola, right? So if you plot it, I hope I'm getting this right. So it goes like this. I think. But anyway, it's a hyperbola. But see what happens when we do another affine chart. If we do a different affine chart, I'm going to do the affine chart with, which one do I want? X equals 1. With x equals 1, I get the curve now 1 minus y squared equals z squared. which is 1 equals y squared plus z squared. So in the this was in the xy coordinates, but if I plot this one now in the yz coordinates, it turns out it's a circle. Okay. So what happens is that in projective, so as a projective algebraic set, this conic, it's not a hyperbola, an ellipse, or a parabola. It depends what chart you choose. That you might see it, that the sort of like the cross section in that affine chart looks like a hyperbola or an ellipse or so on. So in affine geometry, there is a classification of conics into hyperbolas, parabolas, ellipses, but in projective space, they're actually all the same. And those affine images are just that, sort of like shadows of what a conic is in projective space. They're all the same. They're all three are sides of the same coin. Okay. All right. Very good. So we've done homogenization and dehomogenization. Yeah. So this process, by the way, this is going from here to here that we call dehomogenize. Of a projective curve or a projective algebraic set. All right, so let's move on. What are we going to do now? Let's talk then, we're ready to talk about varieties. So here is the definition of variety. So projective, and either affine or projective algebraic set V is called a, again, projective or affine variety if it's ideal, if it's just affine, or homogeneous ideal, if it's projective, is a prime ideal. In K bar X. Okay, so let me write here a line. We're going to do some examples, but before I do some examples, let me say that this definition is actually equivalently, we can say that V is a variety if it's irreducible as an algebraic set. So what that means is that V is not a union of two proper algebraic sets. Okay, so let me show you some examples of all this. So here is examples. First, let's do something simple. So if we start with, remember, X inside Q bar of XY. Oops, we need to be careful. We're not talking about the function field. We're talking about the polynomial ring for ideals. Okay, so that ideal is prime because, for example, the quotient of the polynomial ring by X is isomorphic to Q at join I, and that is an integral domain. So the ideal itself is principal. Okay, it's prime. Excuse me. So yes, this is a prime ideal. Okay. What else did we see? We saw also, for example, the ideal generated by X and Y in Q bar XY. that is also a prime ideal. In fact, it is maximal. When I do the quotient of my polynomial ring by this ideal, I get something that is isomorphic to Q bar, and therefore that is a field. So this is actually a maximal ideal, therefore prime. So this is a prime ideal. Okay. What else? We can take, let's see something that is not a variety, that is not going to define a variety. How about the polynomial, the ideal x times y? Well, that ideal is definitely not prime. X is not in that ideal, y is not in that ideal, but x times y is in the ideal, so it is not prime. And then also, if you do the quotient by this other ideal, then you see that the quotient will have zero divisors, so it's not an integral domain, so this is not prime. Okay, so why is that not prime? Well, the variety this induces, so what is not the variety, it's not a variety, the algebraic set given by this ideal will actually have two pieces, because there can be points that the polynomials vanish because x vanishes. So 0b for any b in Q bar is in there, but also a0 for any a in Q bar is also in there. And then you see that the algebraic set is actually union of two other proper algebraic sets. So therefore it's not irreducible, and that's why it's not a variety. Okay. One more note here, or a warning, is that you need to check primality in K bar. Okay, let me put a few bars there to stress that you have to do it in K bar. For example, if you take the ideal x squared plus y squared in Q, that polynomial is irreducible over Q. But when you look at it over Q bar, this splits. Now x plus iy times x minus iy are factors, and therefore it is not a prime ideal over Q bar xy. Okay, so you have to be careful that this is not prime, and you really are using the fact that we're checking in Q bar. Very good. So now that we have varieties, okay, then we can talk about their function fields. Right. So first, we're going to define their affine coordinate ring. So let V over K be a variety. Then we define two things. The coordinate ring is those functions that make sense for V, in that if I have any function in the function field of projective space, so if I have a function f, but I have another function g that is in the ideal of V, then f and f plus g are going to give me the same values because g vanishes at V. Okay, so what we can do is cut out those redundancy by doing a modulus, doing a quotient by the ideal generated by the variety. So we can take, so I'm going to do k x modulo the ideal of the variety, and that is going to be called the affine coordinate ring. Great. And notice that it's an integral domain because I is a prime ideal, and therefore I can do a field of fractions, and that is what we are going to call the function field attached to V, is the field of fractions of the affine ring. Okay, so this is the function field of V. Great. Very good. So, by the way, what happens if this is an affine variety? What happens if we have a projective variety? If V over K is a projective variety, then the affine ring is going to be the affine ring, by definition, is going to be the affine ring of an affine chart. So just pick any affine chart and take the affine coordinate ring of that. And similarly, the function field is going to be the function field of an affine chart. Okay, so let me do some examples of this. Let's do them up here. So some examples of this are the following. Let's go back to our the example that we had before. So for example, we had these running examples. We had the ideal x and q adjoin xy such that vi is the y-axis. So let's see, what is the function field? What is the affine coordinate ring? The affine coordinate ring of the y-axis will be, so what is q of v? Square brackets first for the affine coordinate ring. Oops, messing up the colors. So that is going to be q square bracket modulo the ideal x, but that is just isomorphic to q adjoint y, which is the polynomial ring in one variable, which is the coordinate ring of a line, of the affine line. So it makes sense that the y-axis would have a coordinate ring that is isomorphic to just the coordinate ring of a line. And the function field will be the field of fractions of this, which is the field of fractions, which is the function field in one variable. Okay. What other did we have? How about the function field of, so let's take an elliptic curve now. So remember, we had this curve. Okay, and q adjoint xy. The algebraic set attached to this is the curve given by this equation. And then the affine coordinate ring is going to be q adjoint xy modulo the ideal generated by this polynomial. And then the function field. Oh, by the way, before I do that, did we talk about, we didn't talk about here, one more example is that. So if I have y squared minus x cubed plus x, is this a prime ideal? And for that, what you can use is that this is a UFD, and you can just check that this is an irreducible polynomial to show that this is a prime ideal. Okay, so I will leave that as an exercise. Show that that polynomial is irreducible of q bar xy to show and then show that this is a prime ideal. So yes, it is a prime ideal. And that tells me then that that this is a variety, okay? And then this is the function field, or this is the affine coordinate rank, and then the function field is going to be given by, well, what are we having? We are having definitely functions in x, and then functions in y, but the y now is a function that satisfies an algebraic relation with respect to x. So I'm going to write it as the function field of x adjoined with x, and also a function whose square root is x cubed minus x. Okay? All right, very good. So that is a function field of what will be an elliptic curve. Very good. What else should I do now? We're ready to talk about the dimension. Okay, so let's go right into that definition. The dimension of a variety, so let V be a variety. The dimension of V is the transcendence degree of the function field over K bar. So that is a field extension, and then we can compute the transcendence degree of that extension. So let me do an example right here, again, with the variety on top that is going to be an elliptic curve. So if we start with my variety being defined by y squared equals x cubed minus x, we've computed that the function field is of this form, is we have to adjoin x and then a function whose square root is x cubed minus x. Okay, so what is the transcendence degree of this extension? Well, we have q bar, then there's a, if you want, an extension or a tower of extensions like this, such that this is an extension of transcendence degree 1, because by definition, all we're doing is adjoining one transcendental element, which is the variable x. However, this extension is not transcendental, because over q adjoin x, adjoining that square root is just an algebraic extension. Okay, so there is only the growth in transcendence degree is only by 1, and this tells me then that the dimension of V is 1. All right. Similarly, you can see that a much simpler example is that if V is what we call before the y-axis, so given by the ideal x in two variables, then the function field was just isomorphic to q bar adjoin y, and therefore that is over q bar, it's a classical extension of transcendence degree 1. So the dimension here is also 1. Okay, great. So then we are ready to define what a curve is. I'm going to take a tiny break here, and then we'll finish in a moment.